Alright, so sticking with section 12.4, today we're going to look at orthogonal and parallel vectors. So remember, this is kind of what I told you to think about at the end of the notes from last night. So we want to further look at some uses for vectors. Specifically, we're going to be looking at how to determine if they are orthogonal or parallel to each other. So what does orthogonal mean? Well, you could probably guess if you don't already know, but orthogonal is another word for perpendicular. So we're looking at our vectors perpendicular / orthogonal to each other. How can we help, or how can we figure that out? Well, one thing we can do is find the dot product of the two vectors. So if we have two non-zero vectors, v and w, they're orthogonal to each other if v dot w equals 0. So if the dot product of two vectors equals 0, then the vectors are going to be orthogonal to each other. We know that 0 dot v, and 0 being the 0 vector, is going to also equal 0. And so what that tells us is the 0 vector is technically considered orthogonal to every vector. So let's think about this for a second before we go into an example. Why does a dot product of 0 lead to orthogonal vectors? And what about parallel vectors? Does the value of the dot product tell us anything about if the vectors are parallel or not? So I want you to pause the video and either write down and explain or show using formulas or an example why a dot product of 0 will lead to orthogonal vectors, and then also think about how the dot product can either tell us or help us figure out if vectors are parallel. So pause the video and try to think about that for a minute, and then unpause the video when you're done thinking and writing. Okay, so hopefully you were able to think about the fact that, well, yesterday we talked about cosine of theta is v dot w over the magnitude of v times the magnitude of w. So if the dot product is 0, then the cosine of theta is 0 over the magnitude of v times the magnitude of w, which is just 0. And then theta would be the cosine inverse of 0, which is 90 degrees. So that would tell us then that the two vectors are perpendicular. So that's why if the dot product is 0, we know that the vectors are perpendicular and we don't actually have to find the angle. What about parallel though? So in order for the vectors to be parallel, theta would need to be what? Well, theta would have to be either 0 or 180. So the vectors could be going in opposite directions. So in order for them to be parallel, cosine of theta would have to equal 1 or negative 1. So it would be 1, it would be an angle of 0, negative 1 would be 180 degrees. Therefore, we know that they are parallel if the absolute value of the dot product equals the magnitude of v times the magnitude of w. So now let's do some examples. First, figure out, are the vectors v equals 3i minus 2j and w equals 3i plus 2j orthogonal? Pause the video, determine if they're orthogonal, unpause when you're ready to check your work. Okay, so we should end up with v dot w is 3 times 3 plus negative 2 times 2, which is 5. That is not 0, therefore they are not orthogonal. Are the vectors 2i minus 2j and 3i minus 3j, are they parallel? So pause the video, determine if they are parallel, unpause when you're ready to check your work. So we have cosine of theta is 2 times 3 plus negative 2 times negative 3, which is going to be 12. So the dot product is 12. And then the product of the magnitudes, the square root of 2 squared plus negative 2 squared times the square root of 3 squared plus negative 3 squared is also 12. So 12 divided by 12 is 1. Therefore, if I did the cosine inverse of 1, that would give me an angle of 0. And I know that they are parallel. Now, another thing to point out, though, because we always want to keep things simple, this is what we would need to do to show analytically that these two are parallel. But hopefully, if you look at the two vectors and you think about how do I draw a vector on my coordinate plane, well, I would go right 2 and down 2 for this vector, and here I would go right 3 and down 3 from the origin. So they would both have a slope of -1, which would mean that they are parallel. Okay, so a couple more examples. I want you to determine, for the first two, are they orthogonal, parallel, or neither? And then for the last example, I want you to find the angle between the two vectors. So pause the video, find out if these are orthogonal, parallel, or neither, and then find the angle between these two vectors. Unpause when you're ready to check your work. Do all three. Okay, so we should end up with the first set of vectors are parallel. We can see that we do the dot product, and in the numerator we end up with -50, and then the product of the magnitudes gives us +50, so the result is -1, and so I know that they're going to be parallel because they would have an angle of 180 degrees, or pi in radians. The second two vectors are going to be neither. When I do the dot product, I end up with 5. When I do the product of the magnitudes, I end up with 5√5, which simplifies to √5/5. I did not necessarily need to do that to answer the question, because as soon as I get here, I can see that it's going to be neither, because it's not 1, -1, or 0. So that's going to be neither. And then for the last one, to find the angle between them, I just go ahead and do the same process I've been doing, but now continue on to actually find the angle. So the dot product produces 27. The product of the magnitudes is 5√34. I didn't rationalize only because my answer is finding the angle, so I don't care about rationalizing to find the angle. If the problem wanted me to find what is the cosine of theta, then I would want to rationalize this problem. But since I'm going to be typing this into my calculator, I do theta equals the cosine inverse of 27 over 5√34, and I get 22.166 degrees. Okay, so we want to understand that this relationship, cosine of theta equals v dot w over the magnitude of v times the magnitude of w, allows us to tell the orientation of two vectors, if they are parallel, orthogonal, or neither. And then no matter what we do, we can always find that angle. But recognizing earlier on that they are parallel or orthogonal might save us a little bit of time.